So hello everyone and welcome to our channel. Today we again have a problem on algebraic geometry in which we are given a certain system of equations and we eventually convert into a geometric problem and evaluate whatever we have to. So today we have this problem with us, which is we are given four variables x, y, z and w, and they are positive real numbers, and they also satisfy this system of equations, and then we have to solve for the largest possible value of this expression, which is xy plus zw whole square. And let's start with the video. So let me write down the equations one by one. 2x square plus 2y square minus xy is equal to 72. So we divide by 2y, that you are just going to see in the next step. Xy upon 2 is equal to 36. And now, as a special appearance in the video, let's invite cosine rule, and you can now see that we have a square term here, xy here, and 6 square here. So clearly we can form a triangle from here by writing it as x squared plus y squared minus 6 squared is equal to xy upon 2. Let's divide by 2xy into 2xy. So this becomes 1 by 4, and so we can convert this into this triangle, which looks something like this. Theta, let the angle be theta such that cos of theta is equal to 1 by 4. This is x, this is y, this is 6. And similarly, the second equation is simply actually symmetric to this, only we have a plus wz here, 2x squared plus 2y squared plus w of z. Oh, my bad. I am very obsessed with x and y's. 2w squared plus 2z squared plus wz is equal to 72. We can write it as y squared plus z squared minus 6 squared upon 2wz is equal to minus of 1 by 4. You can just like add one more step like here, like it, but I have just skipped that part. So this can be converted into a triangle something like this. This side will be 6, this will be w, this will be z, and let this angle be alpha, such that cos of alpha is minus 1 by 4. So we have utilized these two equations, and then we are just left to think upon this particular equation, which actually relates these two equations. We have something related to x into z plus y into w. So how can we connect that? Just see that this side length and this side length are the same. So we can probably convert it into something like this, where this is the common side as 6, this is theta, this is alpha, this was x, this was y, this was w, and this was z. No, wait, since we have xz plus yw, and since you must have seen the thumbnail, I'm going to use the Ptolemy's theorem. So z must be opposite to this, and it actually doesn't matter for converting a algebraic set of equations into geometric figure. So this can be w, this can be z. Yeah, so we have this, and we also know this formula that cos of 180 minus theta is equal to minus of cos theta, which clearly means that cos theta, and since cos theta is equal to negative of cos alpha, which means that theta is simply 180 minus alpha, or vice versa, which means theta plus alpha is 180. And there is a condition which is quite standard, that if the opposite angles are supplementary, then the quadrilateral can be inscribed in a circle. So this quadrilateral is a cyclic quadrilateral. Wow, everything seems great till now. Now let's see what we have to find in the question. We have to find xy plus zw whole squared. But we cannot actually solve this by using some normal theorems. I will use a theorem called the Ptolemy's theorem. Ptolemy's theorem, which is quite a standard theorem in circle geometry. So suppose we have a circle like this, and we have a quadrilateral this. We can join these diagonals. Let this be P, Q, R, and S. So the theorem states that the product of diagonals, which is PR into QS, is simply equal to QP into RS plus PS into QR, which is the product of opposite sides and their sum. And hence we are going to use this theorem in our problem. So I had used GeoGebra and made a beautiful diagram for this. And here is the diagram. So we had this angle as theta. This angle we had as 180 minus theta. This was x, this was y, this was z, this was w, and this side was 6. So now let's use the Ptolemy's theorem on cyclic quadrilateral ABCD. So we have xz plus yw, which we have given our which we are given as 30. So this is equal to yw plus, sorry, my bad, which is equal to xz plus yw is equal to the product of diagonals, which is AC into BD, and we are already given BD as 6, which is 6AC, and this is given as 30. So from here we get AC as equal to 5. Cool. So now we have completed this quadrilateral. This AC is simply 5. And now we are going to do the area stuff like we did in our previous video. So let me write the area of quadrilateral ABCD as area of figure area of triangle ABD plus area of triangle BDC. And now for those who didn't notice, since we are asked the largest possible value, we will consider this intersection angle as 90 degrees. Why? Because the area of quadrilateral is written as half d1 d2 sine of, let's say this angle is beta, sine beta, where d1 d2 are the lengths of diagonals. And if we want to maximize this, we can simply let sine beta is equal to 1, which is only possible when beta is pi by 2 or 90 degrees. So the area of the largest possible area of ABCD will be simply half into product of diagonals, which is 6 into 5. We can write area of triangle ABD as half into xy into sine theta, half xy sine theta, and we can write the area of triangle BDC as half wz sine 180 minus theta, which is equal to sine theta simply. So we have this becomes 15 is equal to xy plus wz into sine theta upon 2. And since we had cos theta as 3 or 1 by 4, we can write sine theta as root of 1 minus 1 by 16, since sine square theta plus cos square theta is 1, and hence we have sine theta as root of 15 over 4. So let's just substitute it here. So we get 15 is equal to xy plus wz into root 15 by 8. This cancels out to give root 15. We get xy plus wz is equal to 8 root 15. And now we just need to square it. So xy plus wz whole squared is 64 into 15, which is quite a tough calculation for me. So I'm not going to do it. So that's our answer. Hope you like the video. Do like, share and subscribe. Thank you.